Alright, welcome to Big Ideas Algebra 2 Honors Section 2.2, Characteristics and Graphs of Quadratic Functions. So today we're going to be looking at how to graph the quadratic functions in each of the three main forms, and that would be vertex form, standard form, and root form. We can talk about advantages and disadvantages of each form and make sure that you're prepared to graph in all three forms. To start with, we're going to just recap a little bit of 2.1, which was what is the parent function for a quadratic equation and how is it graphed. So the parent function for a quadratic is the function y equals x squared. We know it's a quadratic because it's the highest exponent is 2. And we know that if I make an xy table to graph this, I can find some main points that it would go through. We know that 0 squared is 0, and that 1 squared is 1. 2 squared is 4. We also know that negative 1 squared, which means negative 1 times negative 1, would be positive 1. And negative 2, quantity squared, is positive 4. When we graph it, it makes a U shape. I'll go ahead and put in negative 3, 9. And 3, 9 as well. When we graph it, we can see that this makes a U shape, which is called a parabola. And the highest or lowest point on the parabola is called the vertex of the parabola. It's also important to note that the vertical stretch of this A value, which is currently 1, indicates that as I go over 1 unit from the vertex, I would go up 1 unit, and that as I go over 2 units from the vertex, that I go up 4 units. When I change this, and I make the steepness A, because it's going to change and become A for the vertical stretch or shrink, or x-axis flip, in that case, when I go over from the vertex 1 unit, I would go up 1A. And when I move over from the vertex 2 units, I would go up 4 times A, because A would be the steepness. And we would do that on both sides of the vertex, even though I was only showing you on one side. We would do that from both sides. So that's just a little recap of 2.1. We're going to start with vertex form because it's the most closely related to transformation form that we had studied in Chapter 1. Transformation form, if we match this up, we would have A, which is the vertical stretch, vertical shrink, or flip over the x-axis. We're not worrying about B for the time being. The C, which is the horizontal shift to the right or to the left, and the D, which is the vertical shift up or down. You can see that they match up with the H and the K. The reason why we're going to call them H and K this time instead of C and D is because HK actually represents our vertex. So H is the shift right or left. As a minus sign in the formula, it would be a shift to the right. And the K represents our shift or translation up or down. But as it stands in the formula as a plus sign, then that would be the shift up. And the vertex, in vertex form, is HK. That's why we call this vertex form, because we can see what the vertex is simply from looking at the equation in this form. A still remains our vertical stretch, shrink, or flip, but I'm going to call that steepness, just because it's a little bit faster to say. We would not want to call that slope, because the slope is not constant. As you get farther from the vertex, a parabola gets steeper and steeper. So we would just call this steepness, which is not an official mathematical word. So let's go ahead and see what we would get here. Our axis of symmetry then, if I shift the vertex, our axis of symmetry would be x equals h. And our vertex, like I have mentioned up there, is hk. When we go to graph this, the first thing that we would graph is that we would actually put the vertex in its correct spot. So we would graph the vertex, and we would graph the axis of symmetry, which I'm going to label as AOS, that we would graph the axis of symmetry. Those two you could kind of do interchangeably, but we would want to do those first. And then after we have that vertex on there with the axis of symmetry, then we can look at the steepness point and see where it goes from there. We can also find the y-intercept if we need an additional point. That would be optional depending on what our graph looks like and how far we are from the y-axis. So in this example, if I look at the example, I can see that the x minus c, or x minus h in this case, lines up with x plus 2, and then the plus 5 lines up with the k. So I know that in this case, a is negative 1, and then hk would be negative 2, 5. So I'm just going to write that up here. A equals negative 1 for this example, and then the vertex would have to be the point negative 2, 5. So I'm going to start by putting the vertex on there at negative 2, 5, and then I can put the axis of symmetry. The vertex is always going to go through the axis of symmetry. So I know that the axis of symmetry is going to be, in this case, x equals negative 2. Let's see, I can write that right here. Axis of symmetry is going to be x equals negative 2. And then I'm going to go ahead and put the steepness on. So in this case, a is negative 1, which means that we're not stretching or shrinking it, we're just simply, it's been flipped over the x-axis. And although we would flip it generally before we would shift it, it's easier if we go ahead and just think about what the flip would have been, and then now that we've shifted, we can put that in. So because the steepness is negative 1, instead of going over 1 and up 1, I'm going to move over 1 each direction from the vertex and down 1. And instead of moving over 2 and up 4, I'll move over 2 and down 4. And when I move over 3, just because it fits on my graph, and I do want to use my whole graph space, when I move over 3, instead of going up 9 units, I'll go down 9 units. And that's going to give me a pretty good parabola there if I go ahead and graph that. I can see I don't actually need a y-intercept on that because I can already tell that the y-intercept is 0, 1, since it happened to be one of the points I was looking at. So there's a pretty good graph of that parabola. Here's one for you to try. So if you'd like to pause the video and try that, go ahead and pause now. If you've gone ahead and pressed play again because you've had a chance to try it on your own, let's see how you did. So the first thing I would find is that the vertex here would be the point 1, negative 9. And I would go ahead and find 1, negative 9 and put that on there, and that's the vertex, which also means then that the axis of symmetry would be x equals 1. Make sure when you're writing the axis of symmetry that you would write x equals and not just the number 1, because the number 1 is not an equation. Certainly not of a vertical line. So now that I have the vertex and the axis of symmetry, I'm going to put on my quote-unquote steepness points. I can see that the a value is 2. So I'm going to think about what I normally do. I would normally move over 1 and up 1 from the vertex. But because a is 2, I'm actually going to move over 1 and up 2 from the vertex. Similarly, normally in the parent function, when I move over 2 units, I would move up 4 units, since 2 squared is 4. But because we're going to multiply the y values by a, and a is 2, 4 times 2 is 8. So I'm actually going to move from the vertex, when I go over 2 units, I would move up 8 units. And I can see if a third point would fit on there. Usually in the parent function from the vertex, right, if this is the vertex, if I go over 3 units, normally I would go up 9 units for the parent function. But in this case, I'm going to multiply it by the vertical stretch, which is 2, which means I would go up 18 units. from negative 9 y value. That would actually take me to a y value of positive 9, since I want to go 18 units up from the vertex. So it did fit on my graph. And then I'm going to try and get a nice U shape. And careful when the parabolas are steeper, that you don't make them look pointy at the bottom, because they should still be nice and rounded and smooth at the bottom. So hopefully you did that one correctly. Let's move on. The second form is standard form. So standard form is y equals ax squared plus bx plus c. This is maybe a little bit confusing because this is not the same b and c from transformation form. Like c is no longer a horizontal shift and b is no longer horizontal stretch or shrink. These are a different b and c. We're just using alphabetical letters. A, however, is still going to be your vertical stretch, shrink, or flip. In this case, I'm just going to continue calling A the steepness, so that still works. Thinking of it that way still works. And C is the y-intercept. That's all I have right off the bat. From looking at the equation without doing any work, that's all that standard form will tell me. However, we do have a formula then I can use to find the axis of symmetry, and then from there to find the vertex. And that formula is that the x-coordinate for the axis of symmetry is x equals negative b over 2a. Once I've found the x-coordinate of the axis of symmetry, then I'm going to find the vertex. So because the vertex is always on the axis of symmetry, the vertex x-coordinate is negative b over 2a, and the y-coordinate is whatever we get when we substitute that in. So I'm just going to write that as f of negative b over 2a, but all that means is just to plug in the x-coordinate to find the y-coordinate. When we graph this, I would suggest finding the axis of symmetry first and then the vertex. We do know the y-intercept right off the bat. However, if you graph that first, you may confuse yourself and think that that's the vertex, and it's not. So we're going to go ahead and find our axis of symmetry. Then we can find a y value for the vertex so that we know the vertex and we can substitute that in. We can go ahead and put in the y-intercept since we know it off the bat, and then we can finish it out with our steepness points or our a value. So let's go ahead and do our example. In the example, we have y equals x squared plus 6x plus 8. So I can see that a is 1, b is 6, and c is 8. So I'm finding my axis of symmetry. I'm going to go ahead and say in this case that my axis of symmetry would be x equals negative b, so negative 6, over 2a, so 2 times 1, which is negative 3 in this case. So x equals negative 3. I could go ahead and place that on the graph so I know that that's where my graph is symmetric. If I take negative 3, which is the x-coordinate, and I substitute it in, I can get the y-coordinate of the vertex. So I'll come over here where I have room to do that. And I'll say that means the vertex y-coordinate, the x-coordinate I know is negative 3. For the y-coordinate, I'll substitute negative 3 quantity squared plus 6 times negative 3 plus 8. So this would be 9 minus 18 plus 8. Make sure to do your addition and subtraction together left to right. So 9 minus 18 is negative 9, and negative 9 plus 8 is negative 1. So my vertex is going to be negative 3, negative 1. I can go ahead and put the point on there. And it never hurts to label it with a V. You don't have to, but it never hurts. From there, I know that the y-intercept is 8, so I can go ahead and substitute or put that on the graph. And because of the symmetric nature of parabolas, I can see that if that point is 3 units from the axis of symmetry here, that if I go 3 units then the other direction, that I must have another point on the parabola. So that kind of saves me some work because it makes it fairly easy to graph those points on the parabola. So I'm going to go ahead and put that back on, but without my extra little lines there. So I have those 2 points on my parabola, and then I can also put on the the vertical stretch or the steepness points. Since A is 1, that just means I'll go over 1 up 1 from the vertex. I'll go over 2 up 4 from the vertex. And I can see that over 3 up 9 from the vertex is actually what takes me to that y-intercept of 0, 8. And I already have that on there. So it doesn't give me another point, but it confirms the point that I did have, which makes me happy. I can now have a nice, neat parabola. Watch your vertical line test. Make sure that your parabola never comes back in on itself, but always is going to continue passing the vertical line test. Here's one for you to try. If you want to pause your video and try this, go ahead. So if you're ready to go over this, you have now unpaused. Let's go ahead and look at what we have. We have A equals 2, B equals negative 8, C equals 10. So when I find the axis of symmetry, I'll go ahead and say that the axis of symmetry would be x equals negative b over 2a. So that's negative 8 divided by 2 times 2. If I simplify that, that's positive 8 over 4, which is 2. So I have x equals 2 for the axis of symmetry. Then the vertex is whatever I get when I substitute 2 in for x, and then I can find that y value. So that would be 2 times 2 squared minus 8 times 2 plus 10. So this would be 2 times 4 is 8 minus 16 plus 10, negative 8 plus 10, 2. So my vertex in this case is the point 2, 2. Next, I know that the y-intercept is 10, so I can put that on. That's 2 units away from my axis of symmetry, so I can go 2 units on the other direction and go ahead and have that point. And now if I start to look at the steepness or the a value is 2, so I know if I go over 1 unit from the vertex, I would go up 2. And if I go over 2 units from the vertex, instead of going up 4, I would go up 4 times 2, which is 8. And those are the points that are already on there. So then I would just go ahead and complete my parabola and call it a day. There you go, that's standard form. The last form is root form. And it's called root form because it tells us, or it shows us, the roots or the x-intercepts of the quadratic without even looking at doing any math with the equation. So A is still, you guessed it, the steepness, the vertical stretch, shrink, or x-axis flip. But P and Q both represent the x-intercepts. So the point P0 and the point Q0 are the roots, or you can call them the x-intercepts. When you graph, that's great because you can start with going ahead and graphing P0 and Q0. Notice that it's a minus in the formula, so be careful on that, but you can graph your 2 roots. Next, you need to find your axis of symmetry, but because we know the axis of symmetry would have to be halfway in between the 2 roots, we can average the roots to find the axis of symmetry equation. So the x value for the axis of symmetry would be P plus Q divided by 2. Or you can look on your graph and just split the difference. So the vertex is going to be that coordinate, P plus Q over 2. And then just like we did on the last form, we're going to substitute that into the function, which I'm just going to write f of P plus Q over 2. And that's how I would get the y coordinate there. So we're going to start by graphing the roots themselves. Then I can find the axis of symmetry and graph that. And then I can graph the vertex. And then I can graph the steepness points. And that should be enough pieces that I've got a good parabola there. For example, we're going to do y equals 1/4 times x plus 1 times x minus 9. If I line this up with the form a times x minus p times x minus q, I get that p would actually have to be -1 and q would be positive 9. So I know that the roots are going to be negative 1, 0, and positive 9, 0. And I could go ahead and put those on the graph. To find the axis of symmetry, I can either say that x would equal negative 1 plus 9 divided by 2, which would be 8 over 2, which is 4, x equals 4. Or I can look at the graph and I can notice that this is 10 units apart, and if I split the difference then for the 10 units, I would go 5 units either way. So if I go 5 units this way, I get to x equals 4. If I go 5 units that way, I get to x equals 4. And I can just kind of look at the graph and do that instead of calculating an average and working with the algebraic work there. So I would take my roots, split the distance, and say that x equals 4 is my axis of symmetry. Then, to get the vertex, I can take x equals 4 and substitute it back into the function. I'm going to do that up here in this corner where I've got some room. So y, the vertex is going to equal 4 something, right? But y is going to then equal 1/4 times 4 plus 1 times 4 minus 9. So that would be 1/4 times 5 times negative 5, which would equal negative 25 fourths. We know that 24 divided by 4 is 6, so 25 divided by 4 would be 6 1/4 or 6.25. You can put that as an improper fraction, or if you want to put it as a decimal, you can. I'm just going to leave it as negative 25 fourths, but I know when I graph that, that's negative 6.25 for the vertex right there. If it's not on a grid mark, then you should either label it on your graph or make sure that you have it labeled with a V somewhere in your work. Next, I will want to go ahead and put the steepness on. So in this case, the A, or the steepness, is 1/4. That does not mean, like slope, that I would go up 1 and right or left 4. The steepness only works when you adhere to only going over 1 unit in the x and then 2 units in the x, etc. So I know that if I go over 1 unit from the vertex, that I would go up 1/4 of a unit. That actually works out pretty well for me because this currently is at negative 6 1/4, right? Negative 6 1/4. So if I go up 1/4, I land on that nice neat grid mark of the y equals negative 6. When I move over 2 from the vertex, since 2 squared is 4, I would normally go up 4, but now I'm going to go up 1/4 of 4, which would be 1. That takes me to negative 5 1/4, right? Or negative 21 fourths for the y-coordinate. When I move over 3, I would normally go up 9 from the vertex, but instead I'll go up 9 fourths. I'm not going to put that on the graph. That's not a very nice, neat number. I think we can add that in. But when I move over 4 from the vertex, I know 4 squared is 16. So instead of going up 16, I'll go up 1/4 of that, which would be 4 units. So I'll count over 4 from the vertex and move up 4. And instead of negative 6 1/4, that would take me to negative 2 1/4. You can also, if the steepness aspect of it is causing you problems, you could also just substitute in some x values algebraically and you could get some y values. But ultimately, I think if you can master the whole steepness aspect of it, that's a little bit faster in the long run. So there we go. There's my quadratic. I got a bunch of points in there. It's a pretty nice, neat U. I've got the x-intercepts. I've got the y-intercept, so all the important pieces. And here's the last one for you to try. So go ahead, and if you'd like to pause the video, go ahead. All right. If you have now unpaused, hopefully you've had a chance to try this one on your own, and you've determined that the roots would be at the point negative 6, 0 and negative 8, 0, since they are pluses in the formula, or pluses in the equation, but minuses in the formula. Sorry about that. So I'll go ahead and graph those, negative 6, 0, and negative 8, 0. This is one that I don't want to have to algebraically compute the average to find my axis of symmetry, because I know that the axis of symmetry has to be halfway in between, which would be at x equals negative 7. Then I'm going to substitute negative 7 into the equation so that I can find the y-coordinate of the vertex. And so if I do that, I'll do that up here on top, and I would get y equals negative quantity, negative 7 plus 8, times quantity negative 7 plus 6. So that would be negative times 1 times negative 1, which actually gives me a positive 1. So the vertex is going to be at negative 7, positive 1. I can tell that that's going to open down, not only because the a value was negative here, negative 1, but also I can see from my graph that the vertex is above the roots, which means it's going to open down. And now I can go ahead and put in the steepness points. So because a is negative 1, when I go over 1 from the vertex, I'll go down 1. Those are the points I've already got. When I move over 2 from the vertex, I would go down 4. And when I move over 3 from the vertex, I would go down 9 units. The y-intercept at this point is really far off. If I want to find the y-intercept algebraically, I could put in 0 for x, and I would get y equals negative times 8 times 6, and I would get negative 48 for the y value. So if I want the y-intercept, that'd be 0, negative 48, which obviously is not going to fit on my graph. In fact, let's redo that one too. But I am still going to get a fairly nice parabola where I am here, and I could label this without actually counting 48 units down if we wanted to just label that it would go through the point 0, negative 48 and complete that. So there you go. Hope that helps you graph the quadratics from all 3 forms.